Okay, good evening. This is Professor David J. DelosReyes. Okay, my long video format discussion for this evening will be, this is alternating current circuit, and this will now be lesson number 23. Alternating current circuit, lesson number 23. We are running smooth, okay? So I will be discussing tonight another theorem on how to solve a circuitry problem under alternating current circuit, and this will be the so-called Norton's theorem. Okay, let's proceed. Okay, we'll continue. My long video format discussion for this evening, it's August 17, 2023. The time is around 11:14 p.m. Okay. Alternating current circuit, lesson number 23. Okay. The title of the topic for this evening will be Norton's theorem, example problem. The last time around under lesson number 22, I discussed how Mr. Norton's, okay, solve a given problem by using his theorem. So for this evening, I will be presenting a problem, okay? I will give you the same problem that was solved by Mr. Thevenin. And again, for tonight, we will be solving that same problem by using Norton's theorem. And let us see if the final answer will be the same. Okay? Who is the correct one? Will their answers be correct? Maybe it should be, because Thevenin's theorem was a proven theorem already, and Norton's theorem, let us prove for tonight if he will come out with the same answer as Mr. Thevenin's, solving that same problem. Okay, let's proceed. To illustrate a Norton's theorem, okay, I will give you example problem same as Mr. Thevenin, so the load specifications were the same. So I will try to read the problem. Find I sub L in C sub L in the Thevenin's example, okay, by using Norton's theorem, maintaining same load specifications. Meaning to say, from the previous discussion of the Thevenin's example problem, we will be using same load specifications, even the unknown. It will be the same. It's only that the difference will be the solution for tonight will be Norton's theorem. Okay, I will try to give you the figure. We are given an AC circuit here, Z1, C2, C3, and this is CL. The voltage source is alternating. The voltage is 230, angle 0 degree. And the values of Z1, C2, C3, and CL are here. Z1 is 5, angle 30 degrees, ohms. Z2 will be 6, angle 45 degrees, ohms. Z3 will be 10, the magnitude is 10, angle 60 degree, ohms. And ZL is 15, angle 15 degree, ohms. So all the angles are positive, so these are all inductive loads. Inductive, 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 inductive. It could be that all of them are motor loads. Okay? Let's try to bring out the, what we call this, rectangular equivalent of all the impedances. So when we go in the computation of the impedance that we need, okay, we are ready to obtain, or we are ready to bring out the rectangular equivalent. So to make the solution simpler, we will just be using our calculator. Okay, we are given polar, so the rectangular, we could do it. 5 angle 30 degrees, take the cosine, 4.33 plus G 2.5, 6 angle 45. The value of sine and cosine value are the same, so the real part are the same, 4.24 and 4.24. 10 angle 60 degrees. Okay. The value, the rectangular equivalent will be 5 plus G 8.66. Okay. The real part should be higher because 8.66 divided by 5 is more than 1. And the arctangent of an angle greater than 1 is actually greater than 45 degrees, and it is 60 degrees. 15 angle 15 degrees, the imaginary part will be small compared to the real part. So 15 angle 15 is the value of 14.49 plus G 3.5, 3.88. Oh, that is just a part of the solution. We prepare this one, so when we go to the solution, okay, we don't lag behind with the, what do you call this, changing from polar to rectangular. We'll do it immediately, okay? So what's next? Solution number 1 under Norton's theorem. According to Mr. Norton, we will disconnect the load, because what is being asked is the load current passing through C sub L. So for Mr. Norton's, you try to disconnect that load CL, okay? Then try to short out the terminal. We short out the terminal. We remove CL for the meantime, then we put a shorting wire. We shorted the terminal. Okay? So after shorting the terminal, solve for I, capital letter I with the subscript SC, meaning short circuit current. So after removing C sub L, you short the terminal, then compute for the short circuit current on the board. Okay? You are an engineer, so by figuring out the given figure, try to compute for the short circuit current. You try to analyze it, how to solve for it. And if we try to short this one, okay, C3, there will be no current passing through C3. C3 will be bypassed. Right? If we short this one, no current will pass through C3. Instead, the current of passing through C3, it will pass through this one here. It will pass here. It will not pass through C3. Then it will go here, then go back to C1, then go back to A. Right? That's the nature of a short circuit. Because a current will pass through a FAT with lesser resistance. And comparing the short circuit here to C3, this impedance here is greater than this, because actually if it's a perfect short, Z will be equal to 0. So the current will choose with the lesser impedance. So actually if we try to short out this terminal here, it seems we eliminated C3. Right? It is just something like that. We shorted this terminal here, no current will pass through C3, so it seems the resulting figure will be something like this. The component inside will just be simply C1 and C2, because no current will pass through C3 because it was bypassed, right? So if we try to compute for the short circuit current, okay, it's a simple series circuit, okay? Voltage is equal to IZ, right? So if we try to compute for current, it should be voltage over Z. It should be the applied voltage over Z. Z is the total impedance after the shorting, right? And the total impedance is the sum of vectorial sum of C1 and C2. That's why I prepare already the rectangular equivalent of C1 and C2. So if we try to compute for the value of C1 and C2, okay, we are ready with the values, right? We work like an engineer, right? So C1 plus C2 will be 4.33 plus J2.5. And the value of C2 will be 4.24 plus J4.24. Real, that will be 8.27. Imaginary, they are both plus, so they should be plus J, 8.18. And the computation of the current, we needed the value of the magnitude. So we changed this rectangular form to its polar. Okay? We divide 8.18 by 8.57, that will be less than 1. So the angle should be less than 45 degrees, and the angle is 38.80 degrees. We take the cosine of this, we divide that to the value 8.57, what comes out is 10.902. Okay, the polar equivalent of C1 is C2. So by using this formula, that is, it came from voltage equal to IC. The circulating current, or the short circuit current rather, will be 230 angle 0 degree, The given applied voltage is 230 angle 0. It's always 0 because the applied voltage is made as the so-called reference vector. So this is 230 angle 0 all over 10.902 angle 38.18 degrees. Okay, perform the vectorial division. Magnitude, what comes out is 21.907 and the angle should be 0. We bring this up, minus 38.18 degrees. Okay. The current has a negative angle. So this is a lagging current. It is supposed to be, because C1 is inductive, C2 is inductive, supposed to be the current consumed by this, which is the short circuit current after the shorting of this, is 21.097 angle negative 13.18 degrees ampere. Well, we needed this one in the computation of the current passing through IL later, okay, on the third step. Okay, let's proceed with step number 2. Step number 2, short the voltage E and solve for Z sub n. Z sub n is actually the Norton's impedance. As always, it's the same in the Thevenin's. In the computation of Cn and Cth, we short out E. We short out E. So if we short out E, it seems E is not there, right? Okay, then try to compute for the value of the impedance across these terminals here. Right? That's for step number 2. For both Thevenin's and Norton's, in the computation of the open circuit impedance, we short out any voltage sources inside. Okay, then compute for the impedance across this terminal here. It's open circuit already for the computation of the impedance. Right? So if this is open, we short out E. So it seems C1 and C2 are in series. C3 is in parallel with the combination of C1 and C2. Okay, so I place it here. After the shorting of A, the figure will be this, right? This C1, C2, this C3. Obviously, C1 and C2 are in series, right? Right? And the combination of this is in parallel with C3. So if we try to compute for the impedance across this, we term that one as Z with the subscript N, meaning Norton's impedance. And this is actually equivalent to capital letter C with the subscript TH. What we have computed under Thevenin's theorem is the same as supposed to be for C sub n. So C sub n will be the product all over the sum, right? Because it will be something like this. 1 over Zn equal to 1 over the equivalent of C1 and C2. Okay, we will place that at as C1 plus C2. C1 plus C2 plus 1 over C3. And if we try to simplify this one, Cn will be the product of this, okay, all over the sum. If we try to combine this fraction here, it will be this. That's why it's a must that we know what will be the value of C1 and C2. We did that already here, right? So the open circuit impedance, meaning capital letter C with the subscript N, meaning the Norton's impedance, okay, will be the product C1, C2 times C3. It's just a matter of substitution, right? Cn, where's Cn? No, where's C1 and C2? Oh, I didn't place it anymore. Okay, I expedited a little bit. So after the substitution, what comes out for the value of Cn will be 5.32 angle 4.91 degrees. And this is actually same as the Thevenin's open circuit impedance. Okay, I didn't place the value anymore, I just placed the single equivalent. Because this value here is same as Cth from the previous solution under Thevenin's. So Cn under the so-called rectangular form will be 3.46 plus G 4.04. And step number 3, we are now on the step on how to compute for the current passing through C sub L. So according to step number 3 under Norton's theorem, draw the Norton's equivalent and reconnect. Okay, reconnect ZL. So the Norton's equivalent is actually this portion here. Okay? The short circuit current is in parallel with C sub n. Under Thevenin's, the open circuit voltage is in series, but under Norton's, okay, the short circuit current is in parallel with C sub n. Then, according to step number 3, we reconnect the load. Okay, we connect it again. So if we try to reconnect, it seems C sub n and C sub L are in parallel. The last time around, what do you call this? We derived this one already. Okay? Because to derive this one, it will be the product I short circuit minus I sub L multiplied by C sub n should be equal to the product IL times CL. If we try to simplify this one, okay, combine those IL now will be the product I short circuit times C sub n over the sum of C sub L plus C sub n. We know already the short circuit current from step number 1. We know already the value of C sub n from step number 2, right? And the sum C sub L, so C sub n, it's just a matter of adding them. So if we try to combine this one, okay, 21 times 5.32 over the vectorial sum of CL plus CN. Okay, I give you the rectangular equivalent. If we try to combine this one, it will be 19.619 as magnitude, angle 23.80 degrees. I'm still on camera, right? So if we divide this one now, what will come out for the current passing through load C sub L is 5.72. The angle is negative 12.51 degree amperes. So the answer of Mr. Norton's is 5.72. The angle of the current is negative 12.51 degrees. And let us see if this is correct. From the previous Thevenin's example, the computed current of Mr. Thevenin's was actually 5.715. The angle is negative 12.45 degrees. That is from the original Thevenin's solution. So actually they were the same, except for the so-called accuracy. If we try to get just the one decimal, 5.7 is 5.7, right? Right? So they were the same. And for the angle, if we try to simplify this negative 12.51, it's the nearest value is 12.5, right? And for this negative 12.45, this is 5, so we could make this one already as simply 5, right? Okay, so they are both, it's approximately 5.7, angle negative 12.5 for Mr. Norton's, and for Thevenin's solution, it is 5.7, angle negative 12.5 for the Thevenin's solution. So it means that Mr. Thevenin's and Mr. Norton's, according to their theorem, came out with the same answer for the same problem. Okay, that's the importance of the so-called Thevenin's and Norton's theorem. Okay, so so you now know how important theorems is. If you are solving a problem and it will be solved by another solution, the result should be the same. Kaya for this example, Thevenin's solution is 5.7 negative 12.5. Norton's solution, the result is 5.7 negative 12.5. So don't make the mistakes on the what you call this changing from polar to rectangular. Okay, take it easy, okay? Because if you make one mistake on the side, it's all wrong, okay? Okay, so for those of you who are studying electrical engineering, this is for you guys. Or you've been through with engineering and you want to hear a discussion on Norton's and Thevenin's, this is it. This is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share, okay? I will be telling you this one. Try to watch my long video format discussion on alternating current circuit. I will assure you, you will learn something from it. Okay, good evening from Los Angeles, Professor David J. DelosReyes.